In today's session, let me start our session with your mod n counter. So what does mean by modulus in your counter is modulus gives the number of states which are obtained from a counter. For example, if it is a mod 6 counter, so it will have only the states of 6 unique states are obtained from a counter, that is known as your mod 6. Okay, mod 10 means only 10 states are available on a counter, so then it will be only 10 states which are from 0 to 9. If it is 6 means so 0 to 5. So 0 to 5 is total 6 states, unique states, and 0 to 9 is your total 10 states. So these are known to be the modulus of a counter. So now let me start with the designing of your mod 6 counter using your JK flip-flop. Now in mod 6 counter, so first step is we have to find your number of flip-flops. So using the relation 2 power n is greater than or equal to 1. So using your trial and error method, so let me take your n is equal to 2. N, if it is 2, number of flip-flops are 2. 4 is not greater than your 6. So hence we were moving to the n equal to 3. So if n equal to 3, 2 cube become 8. So 8 is greater than 6. So hence the minimum number of flip-flops required to design mod 6 is equal to 3 flip-flops, and number of states are, so which are denoted the initial state. First state is 0 0, second state is 0 0 1, third state is 0 1 0, fourth state is 0 1 1, fifth state is 1 0 0, and sixth state is 1 0 1. As here it's a 3-bit counter, it will give you the 8 number of states and the maximum state which is 2 power n minus 1. So small n minus 1. So which is 2 cube is 8. So minus 1 is 8 minus 1 is 7. So 7 binary number representation is 111. So it will start the count. If it is having 3 flip flop, it will start the count from 00 to 111. But now in this mod 6, so only I need to obtain the states from 00 to 101 as I require only the 6 states. So hence, so for 110 as well as for the 111, so these states on your counter are treated as your invalid states in mod 6. So if we obtain 110 or 111, it has to come back to its initial state. So you should not have this two states which are 110 and 11 in this mod 6 counter. So in order to do that, so let me draw the state diagram only with the 6 number of states. Upon getting the 101, it has to come back to its initial state 00. Now using your excitation table, so let me derive your excitation table of your mod 6 counter. So using the state diagram, if my present state is 0, next state is 1. If my present state is 1, next state is 2. If my present state is 2, next state is 3. Here 3. So if my present state is 3, it is incremented by 1. So hence 4. So if my present state is 4, so next state is 5. So if my present state is 5, it's the, since it is a modulus counter, so 5 is your maximum count. It has to come back to its initial state, which is 0 0 0. So 110 is not there, 111 is not there in this mod 6 counter. Hence these are treated as your X states are invalid. So have to be represented here, don't guess. And the inputs required on excitation inputs are also mentioned. If the states are not there in your counter, so those inputs required are also treated as your don't guess. Next, now just by comparing your present state of QC and QC plus 1, we were going to write here using the excitation table. So in your excitation table of your last slide, we have here given your excitation table, and using this excitation table we were going to write, so QC plus 1, if it is 0 0 0 don't care, if QC is 0, QC plus 1 is 1, 1 don't care, we write. So 1 to 0 transition, we would write your JC KC as don't care 1. If it is 1 to 1, so we will write JC KC don't care 0. So based on this excitation table, we were going to write the values of your JC KC. So 0 to 0, so 0 don't care, 0 to 0, 0 don't care, so 0 to 0 don't care, 0 to 1, so as it is set, so J value is 1, K value is a don't care. 1 to 1, so no change in the state, so don't care 0. So 1 to again 0, so it will be resetted, so the KC is 1 and J value is don't care. So next here we mentioned as a don't care. So the remaining states 7, 6 and 7 are mentioned with the don't care. Next QB plus 1 we will compare. So then we write here JB KB. So 0 0. So here QB value is 0 and QB plus 1 is 0. So 0 don't care on your JB KB. So 0 and your QB plus 1 is 1. So set. So here JB value is 1 and KB value is don't care. Next QB value is 1, QB plus 1 is 1, so no change, so don't get 0 on JBK. So QB is 1 and QB plus 1 is next state is 0. So KB value is 1 and JB value is equal to don't get. Next 0 to 0 on QB, so QB plus 1, so 0 don't get. 0 to 0 is 0 don't get. And these are the remaining two states are don't get. So in the same manner, we are going to write for QA plus 1 based on your state transition of 0 to 1. As this is set, so J value is 1, K is a don't care. 1 to 0, so don't care 1. So here 0 to 1, 1 don't care. 1 to 0 is don't care 1. 0 to 1, 1 don't care. And 1 to 0 is don't. So now just by observing these all the excitation input columns, so we were going to write here the standard SOP expression of each input in terms of your QC, QB and QA. So now if I write those expression in terms of that, so as a sigma m of, so only one minterm is available on your JC column, which is on your 3, so minterm 3, so and your remaining all are don't care. So hence your sigma D of 4, 5, 6, 7 all are don't case. Now, so using your K-map method, so we were going to minimize your function, which is JC, by placing your on your third cell, which is 1, 4, 5, 6, 7 are our don't cases. So then we have got here that JC minimal expression is QB into Q, as we can form a 1 pair or 2 square adjacency. QB, QA are common for this, and QC is different for these two minterms, hence the minimal expression for JC is QB into QA. The same manner, find it for KC. So KC is having the don't case from 0 to 3. So hence here KC is equal to sigma m of, so only one minterm is available on 5, and here the don't case are plus sigma D of 0, 1, 2, 3 along with 6 and 7 are the don't case. So we included here 6th state and 7th state, as here that state is not available from mod 6, so we indicated that as a don't case. So only 5th one is indicated with the minterm 1, so 0, 1, 2, 3, 5, 6, 7 are don't case. So we can have a chance of here doing the 4 square adjacency, which is required. So KC is equal to QA is the same variable for all these 4 minterms, and QC, QB are different, so hence it is not present in your product term. So hence here KC is equal to QA. In the same manner, we will find for JB. JB is having only one minterm on your minterm 1, and minterm 2, minterm 3, minterm 6, minterm 7 are don't care. So minterm 1 is logic 1, minterm 2, minterm 3, minterm 6, minterm 7 are don't care. So there is a possibility of a pair where JB is equal to QC is common, QC is 0, hence QC bar. So QA is common here, common variable for these two minterms. So where QA is equal to logic 1, and hence here the product term consists QA. So JB is equal to product of QC bar into QA. Next, in the same manner, KB is, so only we have your minterm 1 on KB on the third minterm. So next we have don't case on 0, 1, so 4, 5, 6, 7 are don't case. So minterm 3 is 1. So 0, 1, 4, 5, 6, 7 are don't case. So here there is a chance of doing 4 square efficiency required. KB is equal to QA is common, QC and QB are different. In the same manner, we will find for JA. So JA is minterm, we have 3 minterms on 0, 2 as well as your 4. So only 3 minterms, and the remaining all are don't case. So 0, 2, 4. So 0, 2, 4 are placed as a ones, remaining all are don't case, so which can form an octet. So by considering these don't case as ones, so this functional value is minimized with a logical one. The same manner, KA is KA minterms, 3 minterms we have on 1, 3 and 5. So remaining all are don't case. So 1, 3, 5 we will map on your KA with a 3 variable 1, 3, 5 minterms. In the remaining cells we will map your don't case. So KA is equal to logical 1. So upon drawing or minimizing each excitation, we got it. JC is Q by QA, KC is equal to QA, JB is equal to QC bar into QA, KB is equal to QA, and JA equal to 1, KA equal to 1. So these all gives you the present states of your flip-flops and that are connected on your the particular excitation inputs on your each flip-flop. So now we are going to take your three flip-flops of JA flip-flop, JA, KA, JB, KB, JC, KC. So your leftmost flip-flop is your least significant bit flip-flop, JA, your A flip-flop A is your least significant bit flip-flop, and flip-flop C is your most significant flip-flop. Now using that equations, so we are going to draw that logical one. JA, KA equal to logic 1. So hence this is applied with your high signal. A common clock pulse is connected, all are negative edge triggered. So hence a common clock pulse we have connected and given to the clock pulse CP, or common clear also we can use. Next JB is equal to, we got JB is equal to QC bar into QA. So hence we connected from your third flip flop, complemented state of your QC bar is connected as one of the input of AND gate, QA is connected as the other input. So output of your AND gate is connected to the JB input. So which will give you the product. So JB is now it is equal to QC bar into QA. Now if this JB input depends on your third flip flop complemented output along with your least significant flip flop QA output. So KB is exactly equal to the QA value. So we connected from this QA to the KB value. Next, here JC is equal to QB into QA. So we connected QB is one of the input as a product of, so QB and QA. So QA is transferred as one of the input of your this second AND gate, and second AND gate output will give you the product of your QB. QA is applied on your JC. So KC is equal to QA, hence we connected directly from QA as your KC input. So like this, so we are obtaining the mod 6 counter output from your QA output, first flip flop QA output, second flip flop QB output, and third flip flop QC output will give you the third counter, one of the bit. So your mod 6 counter, one of the 3-bit counter. Now, so till fifth clock pulse, it will function like your up counter, but upon reaching that sixth clock pulse, so it has to reset. So for a short duration of time, so your C flip flop, your C flip flop will go to your logical 1 state, along with B flip flop will also go to your logical 1 state, and your on your sixth clock pulse, your first flip flop, your least significant, will come to your 0 state. Now if it comes to 1 1 0 state, so here now immediately, so QB as it is, QB is equal to logic 1. So and your QC is equal previous states of your, let me find here what will be the JB value, what will be the KB value on your sixth clock pulse. So now see here, QA previous state is logic 1. So next on your before your sixth clock pulse, QB value is 0. Before your clock pulse, your QC value is logic 1. So hence here we wrote it as QB equal to 0 and QA is equal to logic 1. QC is also equal to logic 1. Okay. So QC is also equal to, here I have to mention that the QC output is also equal to logic 1. So before your sixth clock pulse, upon having that sixth clock pulse, so it is moved from 0 to 1. Now that will be your next state. So now let me verify here what will be the JC. JC input is a third flip flop input, depends on your previous states of QB and QA. QB is 0, QA is 1, so 0 and of 1 is 0. KC is equal to QA, QA is equal to logical 1 on your before your sixth clock pulse. So hence KC is 1 and JC is 0. Upon getting this sixth clock pulse, so this flip flop is having JC value. So your J input because of QB, QA, so it is 0, KC value is equal to 1. So if KC is 1, so it will reset. So hence QC flip flop, so though it is 1, so in your fifth clock pulse it comes to your 0 state. So it will comes to the 0 state on your sixth clock pulse edge. So next, so coming to your JB value. So JB is depends on your QC bar and QA bar. As QC is 1, 1 bar is equal to 0, QA is equal to 1. So 0 and of 1 will become 0. So KB is equal to QA. So as QA is equal to 1. So here JB value of on your sixth clock pulse, JB value is equal to 0 and KB value is equal to 1. So if we apply 0 1 on your flip flop B on your sixth clock pulse, it will reset. So hence QB comes to your 0 state. The same manner, so JA is logic 1 and KA is logic 1 here. So previous state of your before your 6 clock pulse, your state of your first flip flop or the least significant flip flop is at logical 1 state, and it comes to your toggle state, which is 0 state. Since my J input and K input are 1, so J input K input is 1, it will be operated in the toggle state. Hence QA previous state is 1, it comes to the 0 state. Hence, so upon 6th clock pulse, QA comes to 0, QB also comes to 0, and QC also comes to 0. So hence like this, so it will only have the states of 0 to 5. Upon reaching the 6th clock pulse, again it comes back to its initial state, which is 0 0. Never ever it comes here 1 1 0 as like your up counter, due to the configuration how we connected using these two AND gates to the inputs of passed through your JB and JC values. So it will not have your the 1 1 0 state or your 1 1 1 state, which is the 7th state. So hence here, so we only have your 6 states from which are counted from 0 0 to 1 1 0 1. So in the same manner, let me design a BCD counter of asynchronous decade counter. It has to count only the states of 0 0 to 9 state, and in your 4-bit binary, if you are taking a 4-bit binary, the number of states we can obtain is 2 power 4 is 16 states. So 4-bit counter can count the count sequence from 0 0 to all 4 ones, which are your 50. Total number of states are started from 0, it will have your total 16 states. So the maximum count which you obtain is, so as here it is 2 power n minus small n minus 1. So 2 power 4 is 16. So 16 minus 1 is equal to 15. So hence the maximum count obtained is binary equivalent of 15 is 4 ones. So now, so in this 4 ones, so now BCD counter only has to count from 0 to 9. So 9 equivalent in binary is 1 0 1 1 0 0 1. So upon getting your clock pulse on 10th clock pulse, so which is the state 1 0 from 1 0 1 0 to 4 ones. So these states of 6 states are treated as your invalid states in a BCD counter. As it is called, it only gives us 10 states. So in your decimal number also we have here only the 10 unique symbols 0 to 9. It is also called as binary coded decimal code or your decade counter because of 10 states. So we have another name mod 10 counter because only 10 states, mod 10 decade counter or a BCD counter. It is also known as BCD counter. In order to design this, so asynchronous counter as we prefer here JK prefer, so which is operated under your toggle prefer, hence JK and K are connected to the logical ones. Now upon reaching 1010 state, so we have to enable an output signal which must be equal to 1, and from your 11 to 15 states, so those outputs are treated as your invalid states. So now if I write your the output y, so function as your sum of min terms, so as a function of your qd, qc, qb and qa. So now you can write as a sigma m of, so sigma m of only one min term is there, so sigma m is 1 0, so 10, so plus don't get sir, so 11 to 15, so 11 15 11 12 13 15 14 15 all are 20. So now let me map your function. So by replacing the functional values, so only 10 is 1, okay, and 11 12 13 14 are all don't get. So in order to cover this min term, so qd qb are your product term y is equal to qd qb. So we were going to connect your AND gate. Instead of AND gate, let I connect your NAND gate here, since your reset signal is active low input. So if I connect a reset signal here, so then it will enable with whenever 1010 comes as your input. So 1010, so x3 will give you the 1 output, so and your x2 will give you the 0 output, and x1 will give you the 1 output, and x0. So whenever x1 and x3 are both are logical ones, so these two ones on your NAND gate will generate your 0 output, and that 0 output if you are transferred through your reset inputs, so all the flip-flops will be cleared. So you may not get your 10th state, only it will count only 0 to 9. So this is about our decimal counter. So reset pulse will be activated. When it is activated, that then it will clear your all the flip flops. So it only counts your 0 to 9 states. So this is about our today's session mod counter. In the next session we are going to learn about your the Johnson counter.